Hey everyone, we are back now with page 3 and the math problems for the thermochemistry lecture. Okay, so in our first problem here, we're going to need your calculators. What is the heat involved when 250 grams of water are heated from 25 to 75 degrees Celsius? Okay, we said that our equation is Q equals MC delta T. Now we have 250 grams. Heat capacity of water is a heat capacity you should know. Okay, 4.184 joules per gram degrees Celsius, or you could just write the word degree even, times delta T. And delta T is 75 minus 25 degrees Celsius. So the degrees Celsius are going to cancel. The grams are going to cancel. I'm left in joules. Let's get my calculator on here. Okay, so what do I have? 250 times 4.184 times, parentheses, 75 minus 25, close parentheses. Boom, 52,300. So, 52,000 joules, if I'm paying attention to sig figs. This is going to be 250. Okay? Now, what is the temperature change when 75 grams of aluminum, heat capacity is provided, thank you, absorbs 250 joules? Okay, if Q is equal to MC delta T, then delta T is equal to Q over MC. So I have 250 joules. I have a mass of 75.0 grams and a heat capacity of 0.900 joules per gram degree. And joules cancels and grams cancels. And I go here, 250 divided by 75 equals, divided by 0.9 equals. All right, so I'm looking at 3.7 degrees. All right, pretty straightforward. Don't think those will give you too much heartache. You won't have any standalone problems based on that. You'll use these as part of bigger problems. All right, what is the work when a gas is expanded from 10 to 100 liters at a pressure of 1.50 atmospheres? Now we know that work equals negative P delta V, which equals negative 1.50 atmospheres times. Now, it's expanded from 10 to 100 liters. So the final volume is 100 minus 10, and that's in liters. Okay? No units cancel. And this equals 100 minus 10 times 1.5, and I get negative 135 liter atmospheres, which seems like an odd unit to you, but don't worry, because we do have a conversion factor back here to turn that into joules. Okay. So, if a piston does 50 joules of work at 2 atmospheres applied pressure, how much can you expand a gas? So if work is negative P delta V, I'm looking for delta V, which equals work over negative P. So 50.0 joules. Down here I have a negative and 2.00 atmospheres. Okay, going to need to do a conversion factor. 101.325 joules is a liter atmosphere. So down here I'm going to put 101.325 joules per liter atmosphere. Now joules is canceling, atmospheres is canceling, and I'm going to be left in liters, which is good. Okay? So 50 divided by 2 divided by 101.325. And I'm coming out at basically 0.25 liters. Okay. Now, you're not going to see a whole lot of these, but I wanted you to have one in your notes so that you know what it looks like. Number 5. When we start, this is really a physics lesson. Let's accept that right now. A baseball weighing 0.14 kilograms is dropped from a building top. When it is 250 meters from the ground, it is moving 15 meters per second. What is its total energy? So its total energy, E, would equal its potential energy plus its kinetic energy, which equals, now its potential energy, what's that going to be? That's going to be 0.14 kilograms times the acceleration due to gravity, 9.1 meters per second squared, times its height from the ground, which is 25.0 meters. Now, boom, 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 0.14 times 9.81 times 25, and that is rounding off to be basically 35 joules. Plus the kinetic energy, which is 1/2 mv squared. So plus 1/2, 0.14 kilograms times a velocity of 15 meters per second, which is going to be squared, and that is going to equal 0.5 times 0.14 times 15x squared, 15.74. We're going to call that 16. 16 joules. 16 plus 35, 30. Actually, it was more like 34. I think it was like 34.3. So we're right in the area of 50 joules, maybe 51, depending upon how you round it. Okay? Now, this is a very classic physics question. I guarantee you this will not be on your test, but the ideas behind it are good. You have an empty swimming pool. It's 3.5 meters deep. A kid on a skateboard who weighs 50 kilograms rides down the side of the pool. Okay? So, there's the pool. Okay? 3.5 meters. You got a kid on a skateboard going down. Okay? He weighs 50 kilograms. If he moves with no friction, what is his potential energy before he starts the ride down? Okay, well, his potential energy up here at the top is mgh, which equals 50 kilograms times 9.81 meters per second squared times 3.5 meters. And when I run that, 50 times 9.81 times 3.5, I'm getting basically 16 joules. All right? Now, that's this first part. What is his kinetic energy at the bottom, assuming 100% energy transfer? His kinetic energy is 1716 joules. Because all that was potential has now been converted into kinetic. All right? How fast is he going? Well, we know that kinetic energy equals 1/2 mv squared. So V equals KE, all right, divided by 1/2 take the square root. So 1/2 comes upstairs. That's a 2 times 1715. Now that's in joules. 1716, sorry. That's in joules. So that's a kilogram meter squared over second squared. And the kid weighed 50 kilograms. So kilograms cancels kilograms. And when I take the square root, meter squared over second squared just becomes meters per second. And that is about 8.3 meters per second. Okay, so that's a little bit of background. A lot of that was just done so that you get comfortable using units. Okay, we will not be doing anything like this specifically as a test question. All right, that's the end of page 3. Hope you had a good day.